very excited to introduce our next speaker, Sabrina Corsetti, who is a senior in LSA majoring in physics and math, and a 2020 Goldwater Scholar. And her research has been more focused on particle physics, but she shifted her focus toward pandemic response work, and has been, so speaking of this kind of point about the importance of ensembles and comparing code and sort of collaborative public efforts that compare different models, she's been doing a lot of work on the CDC COVID forecasting hub and contributing projections there. So with that, I will pass it to Sabrina.
Thank you for that. So today I am going to be talking about taking a data-driven machine learning approach to modeling the pandemic. To start, I have an outline of the topics that I'll be covering, beginning with some of the motivations behind my group's research, followed by an overview of the modeling approach that we use, as well as some of the mathematical and machine learning foundations of our model, as well as some of its defining features. Then I'll talk about a way that we can visualize predictions to help build intuition for what we do. Then I'll go over our model's performance in real life and how we've done historically, followed by some ongoing investigations that our group is considering. In terms of our motivations as a group, first and foremost, we, like many others, wanted to understand and forecast the dynamics of the pandemic. And this is both so that we can inform public policy decisions, but also individual decisions. In addition, in pursuing our modeling approach, we wanted to work beyond common assumptions made by pandemic models. And these assumptions can take many forms, ranging from, for example, population characteristics to transmissivity of a disease, and so on. And since these assumptions are common to both mechanistic and machine learning models, we wanted to kind of break free of this mold. In addition, we wanted to focus our efforts based on our group's background and strengths. So we specifically had a background in machine learning and data science from a quite different physics perspective. And we wanted to use this to take a data-driven approach to modeling a pandemic, offering somewhat of a new scientific perspective. In terms of the model that we use, our predictions are made using machine learning, regression specifically. And we make predictions weekly for a wide variety of regions and data categories. So for example, at the United States, state and national level, we make weekly predictions of cases, hospitalizations, and deaths. Similarly, we predict cases, hospitalizations, and deaths for the MERC regions within the state of Michigan. In addition, we provide system-level hospitalization predictions for 3 hospitalization systems within the Grand Rapids region of Michigan. Now, when we provide our predictions to others, we want to make sure that they reach as far and as wide as possible. So we provide them to several sources. The first place that we provide our weekly predictions is the COVID-19 Forecast Hub, the official CDC resource for pandemic forecasts. In addition, we provide our predictions to the Office of the Governor of Michigan in tandem with the Michigan Department of Health and Human Services. And we provide our system-level hospitalization predictions to Metro Health, the analytics team there, where Metro is one of the systems that we make predictions for. One of the main benefits of our model is that it's extremely flexible, which means that while we currently make our predictions using combinations of case, hospitalization, and death, as well as social distancing and COVID testing data, we can very easily expand our model to account for other factors or to even predict new data categories entirely. So for example, we could include vaccines as a factor in making case predictions, or we could pivot the model entirely to predict global influenza spread. Now, in terms of the foundations of our model in machine learning and regression specifically, one of the main benefits of the model that we use is that we're able to make predictions based exclusively on previous data, which means we don't have to make any explicit assumptions about the populations or COVID-19 transmission when we're considering a different region. In addition, our model is able to iteratively generate predictions from predictions, which means we can make indefinite predictions, although we typically stick to about a 4-week range. Our implementation takes place in the 3 characteristic steps of training, testing, and predicting. During the training stage, we train our model to recognize patterns in COVID-19 data. During the testing stage, we take the model and give it new data, and we test its pattern recognition abilities. Then once we have a trained and tested model, we move into the prediction phase where we're able to make predictions based on the patterns that the model has learned from previous data. Some defining features of our model are that it's very similar to traditional methods like ordinary least squares regression, where our predictions are made based on linear combinations of inputs, where essentially we take combinations of inputs with importances assigned to them that help tell how important historical data points are for predicting future data. However, unlike many traditional methods, we introduce something called a penalty into ridge regression, which is something used to increase our model's adaptability. A bit more on these linear combinations and penalties. At the moment, our model uses 35 days worth of previous data to predict each coming day. And the data that we use to make our predictions can vary based on what we're predicting. So for example, we can use social distancing as a factor in predicting cases. And the importances assigned to each historical point determine how much each point contributes to future predictions. And these importances or coefficients are optimized during the training and testing process. In addition, the penalties introduced into ridge regression help us optimize the model. Where in ordinary least squares optimization, what we want to do is simply minimize the gaps between predictions and data during the training phase of our model. However, in ridge regression, we introduce something called a penalty to help penalize large importances being assigned to specific points. And this helps us prevent overfitting, which is a phenomenon best exemplified by this image at the bottom here. On the left-hand side, say we have a data set exemplified by these scattered points here, and we want to fit a model to it. Clearly, this linear model isn't really capturing the general trends of the data. It's not a strong fit. In fact, it's an underfit. Now, here in the middle, we have what's considered a strong fit, in that the predicted curve is passing through the general trend of the data, but it's not reaching too hard to reach specific points. However, if we move farther to the right, we have overfitting, which is what we're trying to prevent, which is where the model becomes so complex that it begins reaching to reach too many points, and it's not quite capturing the general trends of the data anymore. Now, thinking about how we can visualize our predictions, we can start from a mathematical but less visually intuitive perspective. And so we can start by understanding the matrices used to train the model. So for example, let's say we want to predict national cases within the US based on 21 days worth of previous data. And say we have 100 historical data points to help us achieve this, to help train the model. Well, the model wants to look at relationships between sets of 21 days and the 22nd subsequent day. And so what it'll look at, for example, is it'll look at the first 21 days worth of cases in comparison with the 22nd day, and the second set of 21 days against the 23rd day. And it'll work to make this A variable, this A vector, so that it includes the importances assigned to each previous day. And that's how the model learns to make predictions. One great feature of visualizing our predictions through matrices is it shows how simple it is to account for added factors in our predictions, like social distancing and vaccines. All we need to do is expand this matrix here to include new factors, like, for example, 21-day sets worth of relative social distancing. Now, for a more intuitive approach, we can look at a graphical visualization of our predictions. So say we want to predict national cases today, May 6th, using the last 21 days worth of case data. So April 15th through yesterday, May 5th. To do this, the model first needs to learn patterns from old data, starting from the very beginning. So if our time frame, for example, starts on January 26th, the model will first learn the relationship between the first 21 days and the 22nd day. Then the model will progressively work to understand the relationships between subsequent sets of 21 days for predicting the following 22nd day. So we can start seeing these groupings by color from green to blue here, sets of 21 days. And the model works over time all the way to the very end of the available data through yesterday to learn these relationships, until finally it's able to use the patterns it's learned to predict cases today and even indefinitely into the future. One of the great aspects of this visualization is it shows just how similar the approach is to add in new factors to making our predictions. So for example, we have the image I just showed, which is how we can work over time to learn how to make a prediction in terms of national cases for today. But say we want to add in social distancing as a feature to help make these predictions. All we need to do visually is add an extra row here of relative social distancing in terms of percentages. So for example, people's relative amount of time that they're spending at home compared to before the pandemic. And just as before, we can work over time to learn the relationships between these data points and finally make a prediction for today. Now, when we make our predictions using this model, we don't just want to know a single possible outcome. We want to know the range of outcomes so that we can understand all of the directions that the pandemic could possibly go. And a good tool for this is 95% prediction intervals, which are similar to a common concept of confidence intervals. The 95% prediction interval gives us an interval of outcomes that the model will predict 95% of the time. But there's a challenge of how can we define these prediction intervals for ridge regression specifically? Since prediction intervals typically estimate the variance of a model, but when we introduce a penalty into ridge regression, we trade variance for bias, which is a factor typically not estimated in building prediction intervals. The solution that we follow is bootstrapping, which is a method that generates a whole spectrum of predictions based on random subsamples of the data. And then from this spectrum, we're able to gather uncertainties and understand where the pandemic could travel. One great way to visualize this is looking at predictions, both in terms of individual points and as traces in time. So for example, if we want to look at a single day's prediction for cases in the United States, where this is all of our historical data, and we're making a prediction starting February 1st, we can see that our blue prediction doesn't quite hit the true data that followed the prediction point. But our gray prediction interval captures this data, and we're able to accurately understand where the pandemic ended up traveling. Now, looking at our predictions as traces over time, we see a few patterns where the predictions shown in blue against the truth data shown in black tend to fit relatively well, but we do have a tendency to overpredict when the curve starts to dip down and underpredict when the curve starts to move upwards. Taking a more quantitative approach to understanding our model's historical accuracy over time, we can, for example, look at our accuracy in the United States in terms of our average errors up to 4 weeks ahead for multiple predictions made over time. So for example, at each point in time, we can look at our accuracy up to 1 through 4 weeks ahead. And an ideal prediction will fall within the 25% or the wider 50% error boundaries, with our uncertainties covering the true data. Now, breaking down quantitatively what we saw in the previous chart, we see that our predictions for incident cases and deaths in the United States up to 4 weeks ahead, both of these categories are strong. Our case prediction errors up to 4 weeks ahead are less than 50%, and our death errors are less than 20%. In addition, we find that we consistently outperform the forecast hub baseline, which means that we're consistently improving the group prediction being sent to the CDC each week. In addition, we find that our death predictions are generally stronger than our case predictions, and this is because our death predictions are made in part based on case data. And since COVID-19 symptoms take time to progress, we tend to see the case curve lead changes in the death curve by up to about 8 weeks. So by using case curves to inform our death predictions, we can end up getting stronger predictions. In terms of some ongoing investigations that we have, we're currently looking into other applications and methods of our model. So for example, we're looking at modifying our inputs to predict for other illnesses like influenza. And we're even considering switching out our core algorithm of ridge regression for potentially other more complicated algorithms like neural networks. In addition, we're thinking more about our model structure, wondering, can we train individual models to make predictions for all global regions? Or can we train models categorically based on factors like population density to enhance prediction strength for specific regions? In addition, we're looking into the future for applications beyond epidemiology, such as large data set quantitative genetics analyses, or even psychological studies looking to eliminate independent variables. So just some points that I would like to drive home about our model and some of what I've mentioned today. So we've seen that ridge regression allows for data-driven COVID-19 predictions in the absence of assumptions about pandemic dynamics. In addition, our model is extremely flexible in that we're easily able to add new data and predict new data categories. In addition, our predictions are generated through linear combinations of data, where the coefficients of these combinations are treated as importances for weighting historical data for future predictions. And our uncertainties are given based on the random sampling bootstrapping method. In addition, we've seen that our model has behaved very well historically, with national case errors under 50% and death errors under 20%. In addition, we found that our model principles and its execution are applicable not only to other areas in epidemiology, but also other fields more broadly. So finally, I want to give a quick thank you to the symposium organizers for putting together this event, as well as all of the groups and individuals that have contributed to funding and supporting this project. And so with that, if there are any questions, I'm happy to take them.
Fantastic, thank you. I think so. Tom has been answering questions in the chat during, which has been great. So many of the questions I think have sort of been caught, but we have 3 minutes. I think maybe one question I think Tom is working on now, but I'm curious to hear your answers. Like, how sensitive do you think the predictions are to uncertainties in the historical data and the changing uncertainties, like the fact that the reporting rate has shifted over time, as more testing has happened and things like that? What are your thoughts on that?
That's a really great question. And that's actually something that we've been able to observe over time, is that like really any model, our predictions are only as good as our data sets. And so something that we saw at the beginning of the pandemic, for example, is that underreporting led to a lot of noise in the data and a lot of uncertainty in terms of how many cases, for example, were being underreported or being missed in the data. And so what we've done progressively over time is we always try to take the best subsample of the data that we can. So for example, as soon as we could, we stopped using the earliest pandemic data where underreporting was an even bigger issue than it happened to be later on. And slowly but surely, we've only kept to using the most recent up-to-date data, the most strong data possible. And so we always, again, just try to keep to the most up-to-date useful data that we can.
If I can add to that real quick, because the uncertainties are encapsulated already, right? You showed the out to 4 weeks of the uncertainties, and so any terribleness in previous data would show itself up in our ability to predict the future, right? Which we do compare. So
Great. Yeah, excellent.